picking up where we left off with mass defect and energy, this was our kind of mind-blown moment where we looked at the sum of the masses of the protons and neutrons in an atom does not equal the mass of the nucleus. This is what's known as the mass defect, or defect is another word for error. So it's something where we would expect that the whole should equal the sum of the parts, but it doesn't. And this links through Einstein's equation equals mc squared, where a tiny amount of matter multiplied by the speed of light squared ends up producing a large amount of radiation, and that principle ends up being a good explanation for why such a small amount of nuclear material can, you either say it produces a large amount of energy or it produces a large amount of destruction, depending on what application of nuclear changes you're looking at. So in this, it talks about radiation. So what sorts of radiation are produced by nuclear changes? So the general term that means changing elements is this term transmutation. And transmutation really was the goal of the ancient alchemists. Chemistry really got its start by people trying to convert easily accessible elements like carbon or iron into gold. Everybody wanted gold. And so there was an attempt to figure out, could you take iron and somehow convert it into gold, which was worth a whole lot more? Truth be told, you can do that, but certainly not with the technology available to medieval alchemists, but through nuclear changes, either natural nuclear decay and natural nuclear fusion, or by man-made nuclear processes that have created the various elements in the periodic table, like plutonium, that do not exist in nature, we do see transmutation actually happening. So we cycle back to an application of something like the second law of thermodynamics. Thermodynamics usually applies more to heat than it does to other situations, but still the general rule of how natural systems work, and that is moving from unstable to stable. So unstable isotopes, those that do not have an effective number of neutrons, will undergo changes, transmutations, in order to become more stable isotopes. And I say more stable, again, it's a relative term. It doesn't mean that the product of the decay is stable, it's just more stable than what it started with. And so this process of decay, and decay is a natural process when we generally talk about it, and it is a process of fission, which means a splitting of a heavier element into a lighter one, or a breaking down. Unstable isotopes will have a tendency to become stable by undergoing decay and emitting radiation. So, some examples of different types of radiation. So if we start with the parent. So the parent is the unstable isotope that you start with. And let's take an example of radium, whoops, lost my pen. Radium-226. So atomic number 88, 226 is the mass number. And when radium decays, it's going to end up producing as the daughter element, so the one that's produced, it's going to produce radon-222, which has an atomic number of 86. And so what has changed here? Well, we've lost 4 from the mass number. 226 has become 222. So we've lost 4 from the mass number. And then we've lost 2 from the atomic number, 88 to 86. So that is atomic number 2, which represents the element helium. And essentially what we have here is a helium nucleus. So 4 nucleons, 2 protons, 2 neutrons, and this is called an alpha particle. Lowercase Greek letter alpha, or the Jesus fish, as some of my students tend to call it. So this is what we call alpha decay. where radon breaks down into an alpha particle, and then the daughter product, radon, and then because we're forming new nuclei, this would produce energy according to E equals mc squared. So this is what we would call alpha decay as an example of transmutation. If you've got an alpha, well, chances are then you've got a beta. Let me erase all of this. Yay, mostly gone. Make sure we don't make anybody uncomfortable by leftover dots. This example we looked at when we looked at the wonders of quarks, and that carbon-14, the unstable isotope of carbon that occurs in small amounts in your body, carbon-14 decays to become nitrogen-14. And so if we look at what happens here, we have an atomic number that's gone up 1. So we have gained a proton. So that's not radiated, that's still within. So we have 7 protons. Let's work this out. Protons, neutrons, electrons. So we have, actually I'm going to leave that off because we don't worry about that. We have 6 protons, 8 neutrons, and then over here we have 7 protons, 7 neutrons. So we have gained a proton, lost a neutron. So what happened is that neutron, by the one quark flipping its direction, essentially going from up to down, it's going to become a proton and an electron. So the proton stays in the nucleus, making it now nitrogen, and the electron gets emitted, again, along with energy. And that emitted electron, as part of the transmutation of a neutron into a proton and an electron, that is called a beta particle. The kind of cursive-looking B, the Greek letter beta, and so this would be what's called beta decay. So alpha decay emits a particle, helium nucleus. Beta decay emits a particle, a high-energy electron. There are lots of kind of other little, because quarks can do lots of different things and the fermions can do different things. There are some other versions, but the most common examples of nuclear decay are alpha and beta decay, and probably the most understandable. These occur in natural systems pretty commonly. You may even have some in your house because most smoke detectors use an alpha particle source in order to detect smoke, particles of smoke. In man-made systems, we can actually drive the decay of a system. If I take, let's say, beryllium, and we can take beryllium and we can inject some neutrons into it and create something called beryllium-13. And beryllium-13 is not really stable. It wants to be the more stable beryllium-12. And so the neutron that's injected into it will eventually come spitting out. So we have the radiation being a neutron, and then plus some energy emitted again, because we've changed the nucleus, and this is called neutron emission. And neutron emission is a form of moving from unstable to stable. Exists primarily in man-made nuclear systems. It's an important part of the process of creating new elements and nuclear changes, enriching certain elements to be more useful for fission and reactors and things like that. But it's another form of transmutation in kind of a two-way transmutation, in that you create a new element, but that element being unstable naturally spits out any extra neutrons that you put in. So we have alpha decay, beta decay, neutron emission, all forms of particle emission from nuclear changes. And then ultimately, when we talk about this energy term over here that shows up quite a bit, we're talking about electromagnetic radiation. And you've probably heard of this before, the electromagnetic spectrum. And seeing if you remember some of this from like middle school, you have radio waves, you have microwaves, you have infrared, you have Roy G. Biv, the colors of visible light, you have ultraviolet, X-rays, gamma rays, and then actually one that probably was not on your list in middle school is Hawking radiation, which is kind of a new ultra high end of the electromagnetic spectrum that is part of the theories behind black holes. But really we want to look at gamma. Gamma is an extremely dangerous but extremely important part of many high energy nuclear changes. Gamma rays or gamma waves, not a particle. The other forms of radiation are particles. Gamma waves are energy waves. Greek letter gamma, the Jesus fish in a nosedive, I guess. Gamma waves are commonly associated with nuclear transmutations, and gamma radiation is extremely high energy. You know, we get sunburns from UV radiation because the UV radiation penetrates the outer layers of the skin and interacts with it. So it can cause sunburns and skin cancer. X-rays will pass through the soft tissues of our body, but not through bones. So X-rays are used to visualize, you know, bones if you have a broken bone. Gamma rays pass right through you and barely even notice that you're there. They can shred DNA, so they can not only cause mutations that might lead to cancer, but they can also just kill cells, obliterate cells by blasting right through them. So gamma waves, you know, alpha particles are fairly easy to protect yourself from. Even a sheet of paper can block alpha particles. Beta particles are more damaging, neutrons are more damaging, but gamma radiation takes the cake. That if you're exposed to a high amount of gamma radiation, no, you do not become the Hulk, you become dead. So this is one of the major risks associated with working around high energy radiation sources is exposure to gamma radiation. So alpha, beta, neutron, and gamma, four most common forms of nuclear radiation from decay. So some facts about decay: it's a process of fission as opposed to fusion, which is the combining of elements. We'll talk about fusion in a different discussion. The rate at which an isotope decays is called the half-life, and we'll have another activity that goes with this. Half-life is the time it takes half a sample to decay. So let's say that you have a radioactive isotope that's half-life is 1 year, and you have 100 grams of it. So you have 100 grams to start with. After 1 year, you would only have 50 grams. After 2 years, you would have half of half, which is 25 grams. After 3 years, you'd have half of half of half, which is 12.5 grams. So you would steadily lose half the amount over time, and the amount of time that takes to pass is called the half-life. And half-life is important because if you know kind of the amounts of daughter and parent isotopes in something, and you know how long it takes the unstable isotope to decay, you can do a little bit of math and a little bit of study and use that to determine the age of something. And carbon dating is one of the most common ones you hear about, looking at the ratio of carbon-12 to carbon-14 and using that to determine how long ago something was alive. But we can also use that for dating meteorites and rocks and different other things using different isotopes. But we'll have another activity that deals with what's called radiometric dating. And then finally, as we said, you know, people can get involved in the whole natural decay thing. And generally we take a system that works nice on its own and we get in and start playing around with it. And the thing that we learn through, studies of nuclear changes all the way from Marie Curie up and through the Manhattan Project in World War II was that you can accelerate the natural process of decay by synthetically, so by people taking steps to concentrate the isotopes. When you concentrate the isotopes, instead of just each individual atom breaking down and spewing out its radiation, the radiation from one decay triggers several others. And so what happens is that elements that would normally decay in their own good time suddenly get triggered by something nearby, and then that triggers another, and everything multiplies. And so the decay of a sample that might take 1,000,000 years takes 1,000,000th of a second, and that's where you end up with an atomic explosion. And so the minimum concentration is often described as the minimum amount needed for a chain reaction. It's really more than just amount. It's not just mass. It has to do with purity and density and all of that. But the minimum amount that you need to carry out a nuclear chain reaction is called critical mass. You will not find any elements in nature that exist at critical mass. If they were at critical mass, they would have already exploded. So the production of a critical mass is strictly a man-made process. And the goal of that is to speed up the decay process. And decay releases energy, so obviously you speed something up, you're going to get greater energy out of it. If you can speed it up at a controllable rate, then you can use that. You can use that for nuclear power, but if you let that process spiral out of control, you get the nuclear bomb. It's not a tree, it's a nuclear explosion, but that's about as good as I can draw. So that is our main introduction to nuclear decay. A little bit of an image here of the chain reaction that occurs in a common example of an atomic bomb or in a fission reactor. And you can see here what's called a decay chain, where uranium becomes barium and krypton, and in that case spits out a bunch of extra neutrons, which go to the other uranium atoms, and they split, and you start getting all these other splits going on, rubidium, cesium, xenon, lanthanum. So you get this just progressive multiplying of decays that speeds up very rapidly. We'll take more of a look at this. We'll look at the Manhattan Project when a lot of this stuff was discovered, and continue to apply things in class for nuclear changes. So thank you, and have a good day.